All right, we're back, and I thought it would be good to talk a little bit about limits. They're probably going to push you to the limits. As many times as I've tutored Calc 1 or taken Calc 1, every time limits starts the course again, there's always undoubtedly going to be one or two limits that are going to kick me pretty good. So don't beat yourself up. Limits can be really hard. But a lot of the times, they're as easy as plugging and chugging. Sometimes you got to pull out the algebraic trickster moves. But anyhow, let's take a look at what even is a limit. So I've got some function here. It's discontinuous, which means that there's jumps in it. So in other words, we've got the graph comes in this way, and then it digitally jumps up to here with no real warning. So that wouldn't be continuous. A continuous curve it's not gonna have spikes. It's gonna be nice and smooth, and it'll never jump around like these two graphs would. But anyways, there's kind of two different kinds of limits. There's right-handed and left-handed limits, and then there's just limits. So how do we indicate that? Well, if we want to know what the limit is, as let's make this minus 1 in the x direction. As we want to know what the limit is as x approaches minus 1, we need to look at two other kinds of limits. So I'm looking the limit as x approaches minus 1 for this function f of x. We'll call this one f of x, and we'll call this other example g of x. So to know what the limit is as x approaches minus 1 for f of x, we're going to need to figure out some other things. Like, what is the limit as x approaches minus 1 from the left of f of x? So you'll notice for the left I put a little minus sign on the right side of the 1. That means that we're going to approach it from the negative axis, or from negative to positive is from the left. So we're going to the right, but we're coming into the left of the intersection of where we're finding the limit. And then we also need to find the limit as x approaches minus 1 from the right. And so that's also the same function f of x. Now let's figure out what the limit as we approach negative 1 from the left. So we're approaching when x is minus 1 from the left. And you'll notice that it seems that y, as we approach negative 1 from the left, y seems to get closer and closer to minus 2. So we're going to go ahead and say that this limit right here equals minus 2. Because as we approach negative 1 from the left, we approach y equals minus 2. Now, what if we approach x equals negative 1 from the right? So as we keep getting closer and closer to negative 1, you'll notice that from the right, we actually approach y equals just 2. And so we have a difference between our left-handed and our right-handed limits. One of them is a totally different number than the other. And because these don't match, this limit does not exist. The left-handed limit exists, the right-handed limit exists, but limit rules state that if the right hand and the left hand limits don't agree, then there is no true limit there. And it kind of makes sense, because if we're approaching this from both sides, we don't really see where it's going. There's no agreement between the left hand and right hand side. Now you might say, well wait, there's a filled in dot up here and an open dot there. So shouldn't the limit as we approach negative 1x be 2? Because we've got the filled in dot up there, indicating that f of x is indeed 2 when x is minus 1. The problem with that is, though, is with limits, we're not actually looking for the value when x equals minus 1. We're actually looking for what is it approaching as it gets infinitesimally close to x equals minus 1. So we don't actually care what happens at x equals minus 1 in a limit. What we care about is if we keep inching closer and closer, what do we approach? But we never reach it, not with a limit. So in this case, the limit of this as x approaches -1 does not exist. Let's take a look at this problem right here with g of x. So we take the limit from the left, limit as x approaches 0 from the left of g of x, and the limit as x approaches 0 from the right of g of x. And let's take a look and figure it out. So as we're approaching from the left, as we inch closer and closer to x equals 0 without reaching it, we'll notice that we're approaching y equals 0. So in other words, g of x as we approach 0 is actually approaching 0 as well. So that's 0. And as we approach from the right, the closer and closer to x equals 0 we are, the closer and closer we get to y equals 0. Or you could think of that as g of x equals 0. So once again, we get 0 here. The left-handed limit and the right-handed limit agree. Therefore, the true limit as x approaches 0 from either side of g of x is also equal to 0. So there's a limit that does exist. And once again, you might say, well, there's an open dot there and there's a filled in dot up there too. And nobody's going to argue that for this function g of x, when x equals 0, y equals 2. I won't argue that. But what I will say is that limits aren't just about plugging in values, although they can be sometimes. But if we're approaching both of these and we don't have the knowledge of the graph, imagine you had a friend walking over here and you were walking here. You would know where you were going to meet. But of course, with this graph, when you get to the location itself, you're actually at y equals 2. But limits are about how we approach things. And so both of these people are approaching the same thing, and so they're both going to agree that the limit as we keep walking here is at y equals 0, or g of x equals 0. So that is an introduction to what a limit is. I'm going to do a quick talk through about how to solve some limits. There's really two steps to solving a limit algebraically. One of the steps is super easy and the other one is ridiculously hard sometimes. So limits, how do we solve them? Well, my step one, I always do this first, is plug in value. So I've got an example for that right here. This question is wondering what the limit as x approaches minus pi for this function is. So the function is x plus 7 times under the square root times cosine of x plus pi. Alright, so my first step is always plug in the value. I don't want to waste my time if I don't have to. So pi, when I plug in pi to cosine, negative pi for x, right? We're substituting for x. Negative pi plus pi is 0. Well, cosine of 0 radians is 1. So this is actually going to 1. And then we'll plug in negative pi for this x as well. And we'll end up with negative pi plus 7 times the 1 out here. And it turns out this is just 7 minus pi, all under the square root. This is the limit of this. And so that was as easy as plugging in. Now here's another quick technique for a limit that also includes some logic. I wouldn't call it plugging in, but for this problem, oh, and I'm sorry, this last problem I did was from section 2.2 on my math lab, and it was problem 13. So that was the first example. Now we're doing 2.2, question number 18. So what we got going on here is it says if square root of 7 minus 5x squared is less than or equal to f of x, and f of x is less than or equal to the square root of 7 minus x squared. And this is only true for instances where x is sandwiched between 1 and minus 1. The question is, find the limit as x approaches 0 for f of x. And this is honestly kind of really tricky when you first look at it. The more you walk through it, it'll start to pop out more. But what we have here is we have two functions, right? And I'm just going to go ahead and plug in 0 for each of these functions. So plug in 0 for this side. 7 minus 0 is just root 7. And then over here, this x squared goes away. And so we're left with over here just root 7 as well. Well, if f of x is greater than or equal to root 7 and also less than or equal to root 7, this is a case, this is a proof that f of x must equal root 7 at this particular time. And this particular time is at when we're at x equals 0. So the limit as we approach x equals 0 for f of x is equal to root 7, as proven by this, you could call this a sandwich theorem. So in other words, if it's greater than or equal to this, but less than or equal to this, and these two things are the same, you've proven equivalency. So anyhow, I wasn't able to find any very horrible algebraic examples yet, but I'm sure we'll run into some together in the future. But if the plug-in value doesn't work, then you're stuck with step 2, which is algebraic trickery. This can range over a series of topics, whether it's pure algebra. You're going to need to know your trig really well if you don't want to struggle with these problems. Definitely going to need to, especially know how to factor. Factoring is going to be huge here. I know you've done this before, but nothing wrong with brushing up on your factoring skills. So these are a few of the techniques that will help you if it's not as straightforward as plugging it in. And I should probably explain when plugging it in is not acceptable. You may never plug it in. In other words, you can't just plug and chug the value that x is approaching if it creates a 0 in the denominator. The second you create a 0 in the denominator, you've now broken math. And so if you see a 0 in the denominator, that's going to warn you that you're going to have to use some algebraic trickery. So hopefully this helped you with limits. Please feel free to post questions in the comments, shoot me emails, or get a hold of me via text. I'll see you next time.